Hola, buenos dias. That's as much Spanish as you'll likely get out of me today, unfortunately. But hopefully your English is better than my Spanish is. So we'll spend about an hour and 15 minutes or so talking about DNS. You thought you were going to get off easy and you weren't going to have to earn your keep today, but I'm going to move around a lot. So we'll talk about DNS security. In particular, we're going to talk about the latest trends in DNS security, the types of threats that we see to DNS infrastructure out on the internet today. And so that this talk is not just doom and gloom, we'll also talk about various mechanisms that exist for addressing those threats. So my hope is that even if you're not an Infoblox customer, you still get something out of the talk. We'll talk about a lot of mechanisms that work with regular bind name servers, even Microsoft DNS servers, believe it or not. A couple of footnotes. If you're interested in copies of the slides, we're more than happy to give them out, so there's no need to write anything down. If you have any questions, just wave your arm around and I'll turn your way. Okay, so here's what we're going to talk about. We will start by talking about DDoS attacks and their relationship to DNS, and we'll look at a number of mechanisms for addressing them. We'll look at monitoring DNS traffic. We will look at Anycast and a new technology called response rate limiting. Then we'll look at cache poisoning, an old but very serious threat against DNS infrastructure. And we'll look at query port randomization and DNSSEC, the DNS security extensions, which hopefully will be a nice lead-in to a later presentation on DNSSEC. We will look at the threat of malware and a new mechanism in DNS called response policy zones that exists to help combat malware with your DNS infrastructure. And then finally, we'll talk about DNS tunneling, and we'll look at Infoblox's advanced DNS protection. But let's start with DDoS. Everybody knows what DDoS attacks are, right? Distributed denial of service attacks. These are attacks in which someone sends a very, very large volume of traffic at some critical resource on your network. Sometimes they're trying to saturate your connection to the internet. Sometimes they're trying to overwhelm a critical resource. Maybe they're trying to use up the TCP transaction control blocks on your web server or your name server, something like that. Unfortunately, these have become very, very common on the internet. And even worse, with DNS infrastructure, DNS servers have kind of twice the relationship to DDoS attacks. One, name servers, as we'll see, are frequently targeted in DDoS attacks. So they are quite often targeted by people who want to basically disable you, take you off the internet. But name servers can also be used in DDoS attacks in a way that we'll talk about in a couple of slides. So I said that these DDoS attacks target name servers, and in particular, the name servers that they target are what we call external authoritative name servers. These are the name servers that make your zone data available to the internet. For example, the authoritative name servers for Infoblox.com are the ones that you would query if you wanted to reach our website or if you wanted to send me electronic mail. So if someone can sustain a DDoS attack against these name servers, they effectively take us off the internet, right? You cannot reach any internet-facing resources that we might make available. Web servers, mail servers, any other application servers. Now, unfortunately, these are public servers. You can't hide them. It's trivial to find them. Anybody can issue a command like the one you see in the middle of the slide there. Look up the name servers authoritative for some zone that's associated with Infoblox. And that gives them a list of those authoritative name servers. One more command per name server gives you its IPv4 addresses. One more command gives you its IPv6 addresses. Simple, right? The trend in DDoS attacks is very unfortunate. There are two big companies that do cloud-based mitigation of DDoS attacks, Arbor Networks and Prolexic, which is now owned by Akamai. And they also both produce quarterly newsletters that track DDoS activity and the trends that they see in DDoS activity. In two of the latest newsletters that Arbor Networks released, they saw that the percentage of attacks that targeted DNS infrastructure went up from 8% to about 13%. So about 1 in 12, 1 in 13 attacks to about 1 in 7. So DNS servers are more frequently targeted, and the average attack that they track, what they consider, for example, a major attack, is over 100 gigabits per second now, and they see over 100 of those every quarter. That's a very, very substantial attack. We don't have anything like that in terms of our aggregate bandwidth to the internet. Now, DDoS attacks also use name servers or exploit name servers. They do that because name servers, it turns out, make really good amplifiers, not particularly this kind of amplifier, although I thought it was funny that somebody demo-taped an 11 over that. Rather, an amplifier of traffic. Right? Here's an example of using name servers as traffic amplifiers. These are what we call open recursive name servers along the top of the slide. An open recursive name server is kind of a big noun phrase, but it's a simple idea. These are just name servers that accept recursive queries from any IP address. So anybody can ask one of these name servers to look up, for example, the IP address of www.infoblox.com or MX records for gmail.com or what have you. And those name servers will do whatever is necessary to find the answer, maybe querying the root name servers, following a referral from the root name servers to the COM name servers, and so on. And when they eventually get the answer, they'll return that answer to the original querier. But in this case, the querier is this guy down here in the lower left, and he's going to use these open recursive name servers in order to attack the target that you see down here in the lower right. So the way that he does this is he starts sending queries, but not from his own address, from the IP address of the target over here. Now, in the case of DNS, it's really easy to spoof that query. Why is that? It's UDP-based, exactly. It's connectionless. So you don't have to worry about three-way TCP connection setup. You don't have to worry about TCP sequence numbers or anything like that. You just write a bogus IP address into the header of the IP packet. And when that name server does whatever work is necessary to find the answer, he'll respond not to the resolver that sent the query, but in fact to the target. And so we do this over and over again using different open recursive name servers, right? Sending many hundreds of queries, even thousands of queries per second to each one of those open recursive name servers. Now, in this case, if the query is about the same size as the response, that's not a very effective attack. Right? You may as well just send the traffic directly to the target. So if we're clever, we're going to look for a relatively small query that generates a large response. Right? And luckily in DNS, there's lots of opportunity for that. So I'll give you 10 or 15 minutes to read through this. No, I won't. This is a query, in fact, for any type of records associated with the domain name isc.org. isc.org is run by the Internet Systems Consortium. These are the guys who manage the bind name server. Right? They actually develop new versions of the bind name server. So these are good guys. They are not complicit in these attacks. They just happen to have a lot of data associated with that domain name, isc.org. And some of this data you can see these are RR-SIG records. These are associated with DNSSEC, DNS key records, which are also associated with DNSSEC. And they're fairly large. You can see that the R data, the right side of these, is pretty enormous, especially compared with, say, an address record or something like that. So if we count up the bytes here in the response, has anyone counted up the bytes yet? No. We get about 4,077 bytes in the response. The query was about 44 bytes long. So that's amplification of about 93 times. Right? So for every byte in the query, you get about 93 bytes long, or 93 bytes in the response. So you can imagine, if you can send a lot of queries to those open recursive name servers, you can move the burden of conducting the DDoS attack to the open recursive name servers. Let's say, for example, that you're generating queries from a botnet that's under your control, and each one of your bots, conservatively speaking, can send about a megabit per second upstream. Over that megabit per second connection, you can send about 2,900 of those 44-byte queries every second. And that'll result in about 95, actually about 93 megabits per second coming back from the open recursive name server to the target. So every 11 bots you have generating traffic is about a gigabit per second. Now, one thing that I will mention here is that some people say, yeah, but maybe it's hard to find these open recursive name servers, right? Maybe there aren't many of them on the internet. There's actually an organization It's called the Open Resolver Project. And they go comb the internet, sending queries to all of the routable IPv4 addresses on the internet and waiting to see if they get responses, looking for open recursive name servers. And their conservative estimate of how many open recursive name servers there are on the internet is 27 million. It's a very, very substantial number. So not at all hard to find 10 to generate a gigabit per second. In fact, you can easily find hundreds, even thousands. So what do you do about this? How do you defend against this? Well, as with so many problems, the first step to solving the problem is realizing when you have the problem, and you do that by monitoring your DNS infrastructure. You'd be surprised how few people bother to monitor queries to their DNS infrastructure, but that's crucial. So I'll show you a couple of things that you can monitor fairly easily. Aggregate query rate and top queryers, and I'll show you how to do this with Infoblox's appliances, but you can do this with other software as well. If you were running bind name servers, you could still do this. If you were handy with open source graphing packages, for example. So here we're looking at aggregate query rate across 4 different name servers in this Infoblox grid. And you can see that these are quite quiet. If you look over here on the y-axis, you can see that the busiest of these is only handling 125 or 130 queries per second. But what's important here isn't the particular query rate that we're processing. What's important here is that we look at it periodically and that we understand what's normal for our name servers. Because every name server is going to be different, and every organization is going to be different. But what's important is that you know what's normal for your organization and can spot anomalies. You can say, you know what? This query rate, this is 10 times what this name server would normally see at this time of day. And then once you realize that there's an anomaly, you can look into it. Right? You can drill down and say, what's causing this? Why am I seeing so many queries? You can set alerts, for example. You can say, hey, if queries per second ever spikes to a value greater than 100,000 or 20,000 or whatever is abnormal for your infrastructure, I want an SNMP trap. I want to be notified of that. You can also look at things like top clients. You can say, who's querying me? And how many queries are they sending? Normally, you'd see probably a fairly flat distribution across a lot of different queryers. Here what we see is one querier that constitutes 96.6% of the queries that we're receiving. Now what could be causing that? Any ideas? Why would one querier represent 96% of our queries? Right? Well, there's several different possibilities. It could be that it's just a busy server. It could be maybe a mail server, for example, that's sending a lot of email. It could be an application server. Maybe the application has gone a little bit out of control, gone haywire. It could be behind a firewall that's not passing responses back. Or on the other hand, it might be that he's not actually querying us at all, and we're being used as a reflector and as an amplifier, and his IP address is actually being spoofed, and we're attacking him. But you'd never realize this unless you actually looked at this output. Another useful tool in combating DDoS attacks is something called Anycast. Has anybody here heard of Anycast? No? Anycast is a configuration technique that's been used on the internet for a very, very long time, and it allows a distributed set of servers to share the same IP address. For example, it's been used on the root name servers for literally decades. To the uninitiated, it looks like there are 13 root name servers, right? Because they have names like A, B, C through m.root-servers.net, right? A through M, 13 letters, 13 root name servers. Each one of them has one IPv4 address. Most of them also have an IPv6 address. But when you think about it, that doesn't make much sense. How could a network as large and as far-flung as the internet exist with only 13 root name servers? Sooner or later, someone would DDoS the root name servers, right? Well, it turns out that every one of those root name servers is actually dozens and dozens and dozens of functionally identical replicas. And by functionally identical, I mean, if you send the same query to one that you send to another, you get the same answer, right? So how does that work? How do they all share the same IPv4 address, for example? Well, the short answer is that every one of them runs a little routing daemon, typically Zebra or Quagga or something like that. And that routing daemon communicates with the neighbor routers and says, I have a route to this IP address. All that stuff gets mixed up in the internet's routing infrastructure, and when you send a query to that IP address, it's automatically routed to the closest instance of that IP address, right? The closest replica to you. So here are some slides that I borrowed from a friend of mine, the guy who works in London for Credit Suisse, and it shows two instances of an Anycast server, both running at 10.0.0.1, instance A and instance B. And these guys are both running routing protocol instances. They're both communicating with their neighbor routers and saying to 10.0.0.1. Right, so that's picked up by router 2 and router 4, and they tell their neighbors, and that percolates out to the leftmost router, router 1. Then when some client, like the one you see over here on the far left, sends a query to 10.0.0.1, that goes to his default router, and the default router looks at his routing table and he says, oh, I see I've got two routes to 10.0.0.1, one via router 2 and one via router 3, and the route via router 2 seems to be a little shorter, so that's the way that I'm going to send that traffic. Server instance A receives the query, he responds to the unicast address of the client over here on the left, and the client gets his answer. But the client actually has no idea that there are two different instances of the server on the right side of the slide. Right? But he's automatically been directed to the closer of the two of them. There's no reason that you can't do this for not 2, but 3, but 20, 64 different instances, right? So the next question is, okay, I see how that gets me to the closest instance of, for example, a root name server, but how does that protect me against DDoS attacks? Right? And the answer is that from any one location on the internet, you can only query, and therefore you can only attack, one member of an Anycast group at any one time. Let's say, for example, that you have the ability to source a lot of traffic from compromised computers in mainland China, and you want to attack one of the root name servers. Let's say it's f.root-servers.net. So you generate all of your traffic and you aim it at F's IP address. Well, the only instance of F you can talk to from mainland China is the one that's closest to you, right? So maybe it's in Shanghai or Hong Kong. So you generate all this traffic and it sucks it all up in Shanghai or Hong Kong, and maybe it collapses under the aggregate weight of all those queries. But only then, only if you successfully overwhelm that host, can you talk to what was the next closest instance of F. And once you do, all the traffic has shunted away from the one in Hong Kong, and it pops back up because it's not receiving any traffic anymore. So unless you can simultaneously source traffic from all points on the internet at the same time in really, really large volumes, you can't keep them all down. This is like playing a game called Whack-A-Mole. I'm not sure how well this translates into a Spanish audience. You ever seen Whack-A-Mole? Yeah. Need to spend more time at American arcades. Basically, the moles, you know what a mole is? A mole, it's a creature that digs under the dirt and pops up. They pop up here, and you have a big hammer that hangs down here, and when they pop up, you're supposed to hit them with the hammer. It's a good game. So anyway, this is a bit like playing Whack-A-Mole with the root name servers. Now, there's no reason that you can't use the exact same techniques within your own infrastructure. If you have multiple connection points to the internet, you can use it. You can use Anycast to say, I have Anycast instance 1. It's here in Madrid, in Barcelona, in Sevilla, wherever else, right? So one can attack all of those name servers at the same time, but only one of them. So we try to make it very easy to support Anycast within the product, but you can do this with bind on Unix or bind on Linux as well. We just try to make it easy to configure within the graphical user interface. And then the last thing I'll talk about with respect to DDoS attacks is something called response rate limiting. This is a pretty clever mechanism that a couple of guys affiliated with ISC, the Internet Systems Consortium, came up with. We aren't the only people in the world who know that you can get a lot of amplification out of those ISC.org name servers. That output that we saw earlier, the 4,077 bytes. A lot of people were using those name servers as amplifiers in DDoS attacks. They were using them over and over and over again. And the ISC folks thought, well, that's not good. We're not being good neighbors. We should come up with some way so that it would be more difficult to use us in these DDoS attacks. So they came up with this mechanism that they now call response rate limiting. And basically they say, okay, In the event that we are being used in a DDoS attack, we can tell, because what we're seeing is the same query, right? Query for any records for isc.org, because that's the one that gives you the highest amplification. And it'll come in over and over and over again from the same IP address. Now, when DNS is functioning normally, that doesn't happen. Why is that? Why wouldn't you normally get the same query from the same IP address, say hundreds of times per second? Caching, exactly, right? The query is supposed to pay attention to the response. All the records in the response have time-to-live values associated with them, and the time-to-live values are, typically many seconds, if not hours or even days. So you shouldn't hear back from them for at least as long as the shortest time to live on any of the records in the response. So they said, aha, we can build a mechanism that pays attention to that. So here along the top of the slide are the isc.org name servers, the real authoritative name servers. And here's this resolver that's going to try to use them as an amplifier to attack this target down in the lower right. And the difference is that all these isc.org name servers have all these token buckets in memory. Token bucket is a very fancy sounding term for what is really a counter. It's a counter that goes to 5. And you start with 5 tokens. I can't do that with this in my hand. Use 5 tokens in the token bucket. And every time you send a response to a particular querier, you look at his token bucket for that response, and you take a token out of the token bucket. You'll see there's a very exciting animated example here where one of the tokens disappears. Wow. Eventually, of course, the token bucket is emptied, right? Once you send 5 responses, the same response to the same querier, his token bucket is empty for that response. And then you stop sending him that particular response, at least for a little while. You also fill the token bucket at a certain rate, 5 tokens per second or something like that. But effectively, this rate limits responses from these name servers to any particular target to 5 of the same responses every second. And that's not enough to DDoS someone. So it turns out this is actually a very effective mechanism. It's been rolled out, for example, on the root name servers. Here's a graph of what the traffic looks like into and out of one of the root name servers. This is the instance of f.root-servers.net that's in Amsterdam. And you can see prior to implementing response rate limiting, they were being used as an amplifier a lot, right? The green represents inbound octets. The blue is outbound octets. And you can see how much more traffic they were sending out than they were receiving in. After implementing RRL, you can see it's almost the same graph. So the good news is this has now become a standard part of the bind name server. It's also been adopted by a couple of other open source name servers, NSD, and a Czech name server called Not. As upgrade cycles take effect and name servers are upgraded to the latest versions, this should become more and more common, and it'll be more and more difficult for people to use authoritative name servers to DDoS folks on the internet. All right, any questions about any of that so far? No questions yet. Okay, well, let's talk about cache poisoning then. So cache poisoning is a very, very old threat against DNS infrastructure. It's a fairly simple idea. It's just inducing a name server to cache bogus resource records that might map the domain name of a popular website. Could be a bank or a brokerage, insurance company's website, online merchant's website, to a web server that has content that may be absolutely identical to the real websites, right? But it's owned and controlled by organized crime, a foreign government, who knows? And you enter your authentication information there, and your login and your password and your account information is captured by some bad guy and then used later on to charge your credit card or siphon money out of your accounts or what have you. So obviously, a very nasty sort of vulnerability. Now this has been around, in fact, since the 1980s. The first time that we read about this was in a paper that was published by Steve Bellevin, who was one of the pioneers in internet security research back in the 1980s, believe it or not, late 1980s. He withheld publication of it until, I think, 1990 because he was hoping that somebody would fix it, but they didn't. The first time that we saw this in the wild, out on the internet, was in 1997. in something called the Kasparov attack, which is named after Eugene Kasparov, the guy who carried it out. And I should explain that back in 1997, if you wanted to register a subdomain of one of the three big generic top-level domains, com, net, and org, there was only one place you could go. Anybody here old enough to remember where you had to go to register that? The Internet, yeah, the Internet's website. And it was run by a company called Network Solutions. And they would charge you $70, I think, for 2 years of registration, and $35 a year thereafter. So Kasparov believed that was unfair. He said, you guys don't own ComNet or org, so we should be able to charge people to register under ComNet and org too. He wanted a piece of the action. But his entreaties fell upon deaf ears, basically. He wanted to do something in order to highlight his plight. And so he decided, somewhat stupidly, to mount this big cache poisoning attack against popular name servers around the internet. So here's how he did that. He has control over these name servers. These are the alternate.net name servers. Kasparov had joined up with a bunch of like-minded individuals who said, hey, we all ought to be able to charge for registration under ComNet and org. And they called themselves the Alternic, the Alternative Network Information Center. Now he's got control over the alternate.net name servers, and he also has control over a bunch of resolvers. And he starts sending queries to popular recursive name servers around the internet. And he's going to ask them for things like the address of xxx.alternic.net, some domain name that's in his own zone. And this recursive name server has never heard of that name before, so it has to go talk to one of the alternate.net name servers to resolve that. It says, hey, what's the address of xxx.alternic.net? And the alternate.net name server responds and says, here's the address, but it includes, as a special added bonus, the address for www.internet.net in something called the additional data section of the DNS message. Right? Except this is not the right address. This is the address of one of Kasparov's web servers. And all that information gets cached on the recursive name server, and anyone using this recursive name server from that point forward to try to go to www.internet.net goes to the wrong place. Right? They go to Kasparov's web server instead. Now this happened to me actually the night of the attack, and I typed in www.internet.net, and my local name server had been poisoned, so I went to the wrong place. But it was obvious I was in the wrong place. There was a big banner across the middle of the website saying, unfair monopoly, blah, blah, blah. So we should give Kasparov some credit. He didn't do this for financial gain. He did this to highlight his plight. But this could have been devastating, right? Something like this carried out against a bank today, for example, or an online merchant could result in literally millions of dollars of losses. Now, this name server in this scenario is doing something that it should not do. What is that? Well, no, it should be answering, right? But there's something that it's being a little bit too trusting. So what is it doing that it should not be doing here? You didn't realize there were going to be so many questions today, did you? Right, it shouldn't be accepting that data in the additional data section, but how would it know not to? How would it know not to accept that data? It's unexpected, yeah. It's actually unrelated to the question that it was asked, right? So if I ask a question about, I say, hey, what's your favorite color? And you say, for example, I live in Barrio del Pilar, like that. I didn't ask, right? That's unrelated to the question that I asked, so I should ignore that. So we quickly realized, our name servers are being too trusting here, and they shouldn't accept data that's unrelated to the question that they asked. And so we added that functionality to our name servers, and this is 1997, so there are like 10 name servers in the world anyway. So we rolled that out, and then we said, all right, we're done. No more cache poisoning, right? Now name servers will only cache records that are related to the questions that they asked. Okay. Well, about 10 years later, we ran into cache poisoning again. And this time it was related to something called the message ID. And the message ID is kind of deep under the hood in DNS, but it's a simple enough idea. Basically, when you have a name server like NS1 over here, and it sends queries to another name server, it has to specify some things in the query, right? It has to say, this is the domain name I'm interested in, this is the class of data and the type of data, this is the IP address that I'm sending the query to, that sort of thing. But in addition to all of that, it stamps this random message ID into the header of the DNS message, right? And the random number is between, it's 16 bits, so it's between 0 and 65,535 in decimal terms. And when it receives what looks like a response to its query, it checks to see, oh, is this actually answering a query that I have outstanding? Did it come from an IP address that I sent a query to? And also, is it the same message ID that I specified? And if it isn't, it dumps it. It says, this isn't a response to my query. Now, this wasn't meant as a security mechanism, but we always kind of took it for granted within the DNS community that this gave us a certain amount of security, because if you imagine, for example, that you're an attacker, if you imagine that you're some guy, down here, and you're trying to spoof a response from NS2 to NS1, but you're not in the path, you're not a man in the middle, you can't see the query, then you just have to guess the message ID, right? And guessing a message ID between 0 and 65,535, it sounds like a hard thing to do, right? Well, the history of the internet is littered with tales of very smart people who have too much time on their hands. And one of those guys is Amit Klein. Now, Amit Klein was the chief technology officer for a company called Trusteer. They were later acquired by IBM. And I don't know why, but Klein got up one morning and said, you know, what I really ought to do today is download the current version of the bind name server and analyze the pseudo-random number generator they used to generate the message ID. I don't know why he wanted to do that, but anyway, he did that. It's sort of a dirty little secret that when we want random numbers, right, from computers, we have to fake it. That's why a pseudo-random number generator is called pseudo-random and not random, right? Because computers don't like to do random things. Despite the fact that you may see really bizarre behavior from Windows, computers like to do the same thing over and over and over again. So we fake it. We build these things called pseudo-random number generators, and what they do is they look at random areas of memory, and they look at the time on the clock, and maybe they count microseconds between keystrokes, and they jam all of this digital data into this big numerical meat grinder called a hash function. And what comes out is not truly random, but if we've done a good job, is at least unpredictable, right? But what Klein found was that the pseudo-random number generator we were using in bind, not to get too technical on you, it sucked. And if it generated an even message ID, then the next message ID it would generate was not 1 in 65,000 possibilities, it was 1 of 10 possibilities. Now, if you think about this, this is really bad. That means if you can find a name server out on the internet that has one of these flawed PRNGs, and they're still out there, then you can send it a query and you can say, could you go look up something in infoblox.com? And you don't even care about answering the query. You just look at the message ID on the query that it sends to your name servers. And if it's even, you do a quick bit of mathematics, you figure out the only 10 possibilities for the next message ID it's going to use, and you turn around really quick and you ask it to look up something really important, right? Like, Bank of Santander's website or something like that. And then you spoof 10 responses from each of their real name servers, guessing the only 10 possible next message IDs, right? And since you know exactly when the query is going to arrive, you sent the query, you can time those spoofed responses to arrive right on their heels, immediately afterwards. And then you can point it wherever you want to. So, needless to say, we took this very seriously, right? We had to patch a lot of name servers. In fact, they're not even all patched at this point. You still will find some name servers out there. But we had, it was, again, just an implementation flaw, like the cache per F vulnerability, just an implementation flaw. We had better PRNGs available to us. We grabbed one out of the OpenBSD operating system and we grafted it into bind, and then we rolled it out, and we said, all right, now we're really done. We don't need to worry about cache poisoning anymore. Because now you really have to guess a random 16-bit number blindly, and that's hard, right? Well, it turns out it's not that hard. And another one of these very smart guys with too much time on his hand, about a year later, figured this out. And he said, hey, you know what? If I have to guess this random 16-bit number, if I get a lot of guesses, I still have a pretty good chance of guessing correctly. In fact, the way that the name server behaved at the time, this fell into a category of attacks called birthday attacks. Has anybody here heard of a birthday attack? No? Or the birthday paradox? Well, the birthday attack gets its name from this thing called the birthday paradox. And the birthday paradox is actually not truly a paradox. A paradox, you guys know what the grandfather paradox is? Any science fiction fans here? The grandfather paradox says you cannot travel backwards in time, right? That's impossible, because if you could travel backwards in time, you could travel backwards in time and you could kill your own grandfather, right? And if you killed your own grandfather, then you would never have been born, right? And if you would never have been born, you could never have killed your grandfather in the first place. So then he'd still be alive. So that paradox says, no, travel backwards in time, impossible, right? Travel forwards in time, still possible. In fact, we're all traveling forwards in time, but at the same rate. Anyway, so the birthday paradox is just a statistical curiosity. And it basically says that the chances of some two people chosen at random, right, Jose Miguel and I, chosen at random, of having the same birthday, being born in the same month and on the same day of that month, are very poor. That only happens about 1 in 365 times. Right? But if we add more and more people into the mix, chosen at random, the chances that 2 or more of us have the same birthday start to go up pretty quickly. And the reason that happens, if you think about it, is because you start to use up birthdays. So we have here in the audience, I don't know, maybe 40 people, something like that, 40, 50 people. The chances that all of us have different birthdays is calculated from a formula that looks something like this. And the only thing important about this formula is that every time you add a person, you have to take 1 away from the numerator. And if you multiply this out, for relatively small numbers of people, you get surprising results. As of, for example, only 23 people, you've already got a greater than 50% chance that 2 or more people have the same birthday. Right? At 30 people, you've got 70% chance that 2 or more people have the same birthday. Now, that is really, really surprising. My ex-wife, who's a very bright woman, very smart, but was not a computer science major or a statistics major or math major or anything like that. She was actually, you'll be interested to know, she was a Spanish literature major. And she studied here in Madrid for a year. But I've explained this to her, and she refuses to believe it. Absolutely refuses to believe it. She says, no, it ought to take 182 or 183 people, because that's about half of 365. It ought to take 182 or 183 people to have a 50-50 chance that 2 or more of them have the same birthday. And I say, no, that's, even at 100 people, you've got 6 nines of probability that 2 or more people have the same birthday. It's almost inconceivable at that point that 2 or more people don't have the same birthday. She still doesn't believe it, and I'm her ex, so she wouldn't anyway. So I say, there's a Wikipedia article. You can read all about it on Wikipedia. And she says, Wikipedia is all lies anyway, so you probably edited it. So those of you in the audience who don't believe me either, we're actually going to try this here today. We're going to make sure this still works. And the way that we do this is that I usually start, and I'm going to tell you what my birthday is. This is my good faith representation that I'm not simply trying to socially engineer your birthday from you to break into one of your accounts or something. So nobody ever has my birthday. I don't know why that is. My birthday is October 25th. Anybody here have an October 25th birthday? No one ever does. I don't know. People are just not very romantic in January, I guess. All right, so let's start over here. Can we start with you? What's your birthday? July 20th. July 20th. Any July 20th birthdays? No. Okay. And yours? February 5th. February 5th. No February 5th birthdays. And yours? November 3rd. Oh, there we go. Look at that. And you're almost sitting next to each other. Well, you can exchange contact information. Send each other an e-card. Well, that didn't take very long. Usually I at least get a chance to get a drink or something. All right, so the reason that this is relevant, not just a parlor trick, is that even though there are many, many more message IDs than there are birthdays in the year, if you get a lot of guesses, there's still a pretty good chance that you're going to guess correctly. So that's what Dan Kaminsky, who figured this out, knew. He said, hey, you know, if I get hundreds of guesses at the outstanding message ID, I still have a pretty good chance of guessing correctly. So I just have to come up with a scenario in which I get a lot of guesses at that outstanding message ID. So here is the Kaminsky vulnerability, discovered in 2008. So Dan is going to play the part of the hacker up here in the upper right. These are the real PayPal.com name servers down here. They have not been compromised in any way, right? But they're going to receive some queries and they'll send some responses. And this is the recursive name server whose cache Dan is going to try to poison. So he starts by sending a query to the recursive name server, and he says, okay, what's the IP address of q00001.paypal.com? Just some random label, .paypal.com. And the recursive name server says, I've never heard of that before, so I'm going to have to ask one of the paypal.com name servers, hey, what's the IP address of q00001.paypal.com? But immediately after sending the query, Dan started pouring in spoofed responses. And he's spoofing the source IP addresses of the real PayPal.com name servers, which you can find out trivially, right, using dig or NSLOOKUP or anything like that, right? And he can spoof them very, very easily because it's all UDP-based. And who knows how much time he has, right? It's going to take some time for the query to get from the recursive name server to the PayPal.com name server and the response to get back. So he can send, you know, maybe hundreds, maybe thousands of spoofed responses. And he's just trying to guess the message ID. He doesn't see the message ID that was sent from the recursive name server to the PayPal.com name server, so he's just guessing, right? Now, maybe he doesn't guess correctly. If he doesn't, then the real PayPal.com name server responds and says, but there is no such thing as q00001.paypal.com. And of course, that response has the correct message ID because the real PayPal.com name server saw the message ID in the query. He just had to copy it into the response. And if that happens, then even if Dan subsequently guesses the message ID correctly, it doesn't matter. His will be dropped as a duplicate response. But Dan doesn't care. Then he looks up q00002.paypal.com, q00003.paypal.com, and he keeps going until ultimately his response beats the legitimate response from the real PayPal.com name server, and he guesses the message ID correctly. Right? Now, some people look at that and they go, yeah, but that could take a long time, right? The thing to remember is that name servers are really, really fast, right? Name servers process tens of thousands of queries per second. And in this case, that speed works against us. So one of the better scripts that we saw come out after the details of this vulnerability became public would take about 10 minutes on average to poison arbitrary data into that recursive name server's cache. 10 minutes. Now, there's one other thing here that's a problem. There's one other way in which Dan has not yet done anything useful. What is that? Anybody? This is not yet a dangerous vulnerability, but why? It's the name, right? If you manage to poison a response that's about q00005.paypal.com, who cares? People go to www.paypal.com or paypal.com. But Dan is very, very clever. Dan said, you know what? I don't have to send an answer. I could send a referral. And the referral would look like this. It could say, well, you asked about q00001.paypal.com. Turns out that is in a delegated subdomain of paypal.com served by a name server called www.paypal.com. And here is www.paypal.com's IP address. On a bind name server, in 2008, even if you already had the address of www.paypal.com cached, that would overwrite it. So 10 minutes to poison arbitrary data into a recursive name server's cache. We were incredibly fortunate that Dan is a white hat hacker, and he let us know within the DNS community about this very early so that we could work on fixing it before it became publicly known. Because this is what we call a game over vulnerability. If you can't fix this, you can pack up your internet and go home. Because you cannot use the internet to do anything safely unless you can fix this. So what we wanted to do was just say, the message ID is too short. Let's make it longer. Let's make it 32 bits long or 64 bits long. But you can't do that without breaking backwards compatibility with every implementation of DNS ever written. So we added randomization in the only other place we could, which is in the query port. And to explain this, I have to say that up to this time, before the Kaminsky vulnerability, if you were a recursive name server and you had to send queries to another name server, you would just ask the operating system for a port when you started up. You'd say, hey, I'm going to have to send queries to other name servers. Can I have a port? And the operating system would hand you a port. And it looked kind of random. It looked like, whatever the next port that was available was, 5921 or whatever. But then you would use it over and over and over again. Every query that you sent to a remote name server would come from that port, 5921 or whatever. So if you wanted to try to spoof a response to that name server, you just had to see which query port he was using, and you'd aim your spoofed responses there. So after the Kaminsky vulnerability became public, we said, all right, we're going to change that behavior, and actually when the name server starts up, we are going to have it ask for thousands of ports from the operating system. And every time it sends a query, it's going to choose another port at random to send the query from. And it's going to keep track of which queries it has sent from which ports. And it will only accept a response if it comes back to the same port that the corresponding query was sent from. So in one fell swoop, we made it thousands of times more difficult to poison a name server's cache, but not impossible. And another one of these smart guys with too much time on his hands, a Russian security researcher named Evgeny Polyakov, proved this. And he set up a name server on a gigabit per second LAN, and he attacked it from 2 workstations. And it took him 10 hours to go through half of the 4 billion combinations of message ID and query port, but he poisoned it. And the problem is that while 10 hours is certainly much better than 10 minutes, it's not good enough. Because if it is really valuable for some hacker to poison your recursive name server's cache, he will keep it under attack 24 hours a day. And your name server probably won't even tell you that it's under attack. Most name servers aren't instrumented to tell you that. And what does it cost the attacker to keep you under attack 24 hours a day anyway? Nothing. He's using your next door neighbor's infected machine to attack you from, right? He's not using his own resources. So we've bought ourselves some time, and with that time, we need to fix this problem once and for all. And the way that we do that is with DNSSEC. Now, I'll just talk very briefly about DNSSEC, but DNSSEC has been waiting around since the 1990s, believe it or not. Right? It's that medicine that is so bad tasting that you want to make sure you're really sick before you take it. But DNSSEC adds asymmetric cryptography, also called public key cryptography, to DNS to allow you to digitally sign zone data in the same way that you might digitally sign an email message. And then someone who understands DNSSEC can use cryptography to validate that data, right? And by validating it, they prove that it's authentic, right? That you were the person who really signed it, you vouched for it, and also that it has not been modified since it was signed. But this does not come cheaply, right? So we have to have lots of new resource record types. We saw some of these in the ISC.org output before. We have to add these records to signed zones, and they're big records, right? We saw those RRSIG and DNS key records. They're gigantic. So our zone data is going to get much larger, typically about 4 to about 10 times larger. We have to add new fields to the DNS message header, and probably the most difficult, we add all of these new administrative processes. So for example, when we generate keys or when we sign a zone for the first time, we have to generate key pairs, and then we have to add the key pairs to the zone, and then we have to run the signer, and then a 10 or a 12-step process if you're using the manual tools to do it. Anytime you make a change to a signed zone, you also have to re-sign the zone, because if you make changes, the signatures obviously have to be updated. Even if you don't change the zone, periodically it has to be re-signed because signatures have lifetimes associated with them. And before those lifetimes expire, you have to regenerate them. So it's a non-trivial exercise. Here is an example of an unsigned zone. This looks almost too small to read, but you can see there are only 5 resource records here. Very simple zone, obviously. So we're going to do nothing with this zone except for signing it. Right? This is functionally the equivalent zone except signed. And there it is. except that's just the first slide. That's the second slide. You can see it gets a lot bigger. And you can see how large some of these records are. This is an RR-SIG record, which is a digital signature covering the DNS key records in the original, or in the zone. You can see how large that R data is. Here are the DNS key records, which encode the public keys for the zone. Very, very large. Right? And I said the administrative processes get more cumbersome. One of those administrative processes is rolling over keys, which you have to do periodically. If you use a private key too many times, it's possible for a bad guy to accumulate all of the encrypted data that you've generated with that private key, and through brute force methods, figure out what private key you're using. So a cryptographer would say, well, you have to roll over periodically to a new private and public key then. But with DNS, because of caching and zone transfer latency, you can't just throw away the old key and add the new one. It's possible that somebody out there in the world has your old data cached and will need the old public key in order to validate it. So there's this multi-step process involved. This is actually copied from the Microsoft documentation. And you can see it's a step 0, 1, 2, 3, 4, 5, 6, 7-step, truly an 8-step process because they cheated and started with step 0. So it's an 8-step process in order to roll the key over. And some of these steps are things like, after resigning, wait for a period of time equal to the max zone TTL value. Well, the max zone TTL value, that's Microsoft's shorthand for the longest time to live of any record in the zone. So maybe that's hours or days, depending on what your zone data looks like. You can't move on from step 3 to step 5 until waiting for hours or days. What if you have to roll over keys for 100 zones? What do you do in the meantime? I don't know. So from the beginning, I've thought that this really means that you have to automate this process. These administrative processes need to be automated. You cannot do this manually. If you do, something is going to go wrong. And in fact, that has happened repeatedly on the internet. Right? Smarter people than I have made big mistakes with DNSSEC. In fact, one of the first times we saw a high-profile failure of DNSSEC out on the internet, the zone that had been signed was nasa.gov. So if the folks, the rocket scientists at NASA can't handle DNSSEC, then we mere mortals should not be expected to. So Infoblox has done a fair amount of work in this regard. We spent a lot of energy trying to automate DNSSEC to the extent possible. Most of the configuration happens right here. And in fact, this is even more daunting looking than it really is in real life. If you want to start signing things using DNSSEC, you can check that box that says send DNSSEC signed responses, and you can check that box that says enable DNSSEC validation and go to town. If you want to sign a zone, you select the zone and you click on a button that is labeled sign zone, and it's signed. And what do you know? If you modify the zone, we know you modified the zone, so we'll re-sign it for you, right? If if the signatures are about to expire, well, computers can tell time, so we re-sign it for you. So we automate the administrative processes really to the extent possible. All right. And that brings us to malware. Now, malware is interesting. Malware has traditionally used DNS as a punching bag. It sort of wakes up, it rides onto the inside of your network on somebody's laptop after it's been infected when somebody visited a website that they shouldn't have visited or installed a piece of software that they shouldn't have visited. And the malware wakes up and it says, aha, I need to find my command and control server. Or I'm going to take all the files on this guy's hard drive and I'm going to exfiltrate them somewhere. So I'm going to find out the IP address of a drop server out on the internet to exfiltrate them to. Right? So it uses DNS to do that. And in fact, it even uses DNS to evade detection. If your malware were always connecting to the same IP address out there on the internet, you'd pretty quickly figure that out and you'd block that IP address. So instead, the malware does a lookup of a domain name, and whatever IP address that happens to map to, that's the command and control server. And so that you don't block access to that domain name, it'll even have a compiled in list of domain names that it runs through to find an active command and control server. And if that's not bad enough, they come up with things like domain generation algorithms that are algorithms that synthesize new domain names to be looked up to find a current command and control server or drop server or whatever, right? So those same guys who came up with response RRL, response rate limiting said, you know what? There are all these organizations out on the internet today that do analysis of malware, right? They reverse engineer the malware, or they examine the domain generation algorithms that they use. They look at the compiled in lists of domain names. But in aggregate, what we have is this gigantic database of domain names we know are malicious. We know that these domain names are directly associated with certain species of malware. And if we could move this database of domain names close to our recursive name servers, we could say, if you receive a query for one of these domain names that we know is used by that malware to identify a command and control server, we can say, don't answer it, right? Or lie, pretend that domain name doesn't exist, or pretend it's the IP address of our honeypot, so you can redirect the malware there and we can see what it's trying to do. Moreover, tell us who tried to look that up, because that's a very strong indication that they're infected. So what they came up with is something called a response policy zone. And a response policy zone is just a zone, like any DNS zone. The difference between that and a regular zone is that the contents of the zone are interpreted as rules. And the rules say things like, if somebody tries to look up this type of data for this domain name, don't give them the right answer, give them this error in response, or give them this other IP address in response. So the way that these are generally used looks something like this. You have some master name server out on the internet run by somebody who provides a feed of RPZ data, and you configure a recursive name server to be secondary for that zone. So that means they pull a copy of it via zone transfer. It also means you can get copies very quickly, because you can use notify to let people know when the zone data has changed. It means you can get copies very efficiently, because you can use incremental zone transfer to pick up just the deltas to the zone data. And then when some client, like this guy here, sends you a query, you look up the domain name and the type of data that he's trying to look up in the response policy zone, and you say, is that in there? And if it is, you send him back an error. You say, that doesn't exist. Or you say, that's this IP address, not the real one. And you log the fact that he tried to look that up so that somebody within IT security can go fix him later. This is not a substitute for an internet firewall, but this is often a more effective place to combat certain types of malware. So you can get these RPZ feeds from lots of different organizations. Infoblox provides a commercial RPZ feed that's aggregated from 30-odd different sources around the internet today, places you've heard of, DShield and Shadow Server and things like that. Other folks like Spamhaus and Serble, organizations that have traditionally been in the DNS blacklist business, now also provide data via RPZ. And there are new commercial entities like Internet Identity and Farsight Security that provide this data as well. And of course, you can all manage it within the graphical user interface. Very exciting. So the last thing I'm going to talk about is something called DNS tunneling. So DNS tunneling is just tunneling data surreptitiously into a network or out of the network using DNS as the channel. And there are a number of reasons that somebody would want to do this. One is that that channel, if it's DNS, is not widely observed. People do not pay attention to the queries going through their DNS infrastructure, right? So you can do a lot of very nasty things using DNS as a channel, and no one will be the wiser. Also, DNS is almost always available. From within almost any network, you can generally look up internet domain names, and that's all you need to do in order to be able to tunnel data into and out of the network. You may not be able to, for example, connect via TCP from some arbitrary internal IP address within the network out to the internet, right? Maybe all of that traffic goes through a proxy server, but there's a good bet that the DNS servers will resolve internet domain names. So here's how this works. You can do a number of really nasty things with DNS tunneling. For example, let's see. Is this still working? Yeah. This is your infected host over here on the far left. And this guy has no direct connectivity to the internet at all, right? But he's been infected with some malware. And this is the recursive name server that he is configured to query. This is the forwarder that recursive name server uses. And this is the hacker.org name server out on the internet. So the infected host wants to bring in some code from this name server out on the internet, right? But he has no way to connect to it directly. So instead, he sends a query to the local recursive name server, and he tries to look up text records for 0.newmod.hacker.org. And that's transmitted up to the forwarder. The forwarder queries the hacker.org name server. The hacker.org name server responds with a bunch of text records. And the text records look like this, right? Text 0.some unique ID dot a bunch of base64 encoded data, 1.id dot base64 encoded data. The base64, that's just a mechanism for encoding binary data in text, right? And within this text, do you know how long a text record can be? Anybody here know how long a text record can be? I was amazed, and I wrote the book, for God's sake. I was amazed because I was doing a little bit of research on this. They could be 65,000 bytes long. Pretty damn long. So, and you can of course have multiple text records as well. That is a lot of data. And then if it won't fit, if whatever you're trying to transmit down to him, whatever binary image you're trying to transmit down won't fit in one DNS message, then he just looks up 1.newmod.hacker.org's text records and 2.newmod.org.hacker.org's text records. And he keeps going until ultimately he gets whatever it is that you're trying to send down to him. So probably nobody's going to realize what's happening because nobody's looking at the stream of queries that's headed out to the internet. Nobody will realize that this is going on. Now, what about exfiltration? What about malware that's trying to shunt data up to the internet? It's trying to take the contents of the hard drive and move it all off to the hacker.org name server here. That would seem harder, right? Because we can send queries for data that's hosted on the name server out there, but how do we move data upstream? And the answer there is, well, we encode it in the query name. Now, the labels of a query, or the labels of a domain name in a query can be up to 63 bytes long. And the entire domain name can be a total of 255 bytes. So it's a little less efficient, but you just put base 32 encoded data in the label of the domain name in the query. Right? And you can put several of them in there as well. Base 32 encoded because you don't want to, you don't want to accidentally trip up the name server putting really weird characters. Base 32 is restrictive enough so the name server is not likely to have a problem with it. And that gets forwarded up to the hacker.org name server. He unpacks that and he says, oh, okay, this is 0.some base 32 encoded data some unique ID. So I've got the first part, and then he sends back a response, NX domain, there is no such thing, which you interpret as just an acknowledgement that he's received it. And then you go on and you send the next piece, right? The next 63 bytes. And you just cycle through that until ultimately you've got all of the stuff exfiltrated. Now this looks sort of hypothetical. I realize that you're probably looking at that and go, yeah, okay, maybe you could do that, right? No, this happens all the time. A friend of mine, Dave Dagan, who's one of the preeminent DNS security researchers at Georgia Tech, has gotten into the business of registering domain names used by malware if the bad guys let them become available. So if you forget, the bad guys forget to pay their registration fees for hacker.org, he runs out and registers them. And this is one of the things he sees regularly. Queries coming in for these really weird-looking domain names, and if you look at what's encoded in the domain names, it's a bunch of data. It's a bunch of patent data being exfiltrated out of somebody's internal network. So the other thing that I'll mention about this is that it looks hard, but you don't have to do it yourself because there are lots of packages available for doing it. Lots of open source available. Actually, I don't know what the licensing is, but anyway, lots of freely available packages that implements DNS tunneling. So this is an area where Infoblox has spent some energy. We have our new advanced appliances that help to combat these threats. And I'll just say very briefly that these incorporate network processors, basically intelligent network information cards that have dedicated compute capability on them, and they examine every single packet that's received by the name server and subject it to this dynamic rule base to say, is this malicious data? Is there something wrong with it? Is somebody trying to tunnel data? And it can do things like say, wow, that's a lot of queries for text records. That's really odd. Normally I don't see that many queries for text records, in the same domain name. Looks like tunneling. Maybe I'll put an end to that. Those are interesting looking domain names that you're looking up with really long labels that have a lot of entropy associated with them, and it can stop that as well. And they'll also help combat things like cache poisoning attacks, DDoS attacks, malformed DNS messages, and so on. Just to give you an idea, this is what one of these name servers can do against a DDoS attack. We had a sort of constantly ratcheting up level of DDoS traffic that we sent to 3 different types of name servers, one of our own appliances, a regular bind name server, and a Microsoft DNS server. So, just stair-stepping the attack traffic up. And then we also sent a stream of legitimate queries to the name servers to see how many of those legitimate queries they would be able to respond to while they were under attack. And you can see that the bind name server does okay up until the traffic reaches about 50,000 queries per second, maybe 72,000 queries per second. And then it's only able to handle about half of the legitimate queries offered to it. The Microsoft DNS server, unfortunately, once you hit about 72,000 garbage queries per second, pretty much can't handle anything. It takes what is affectionately known as a dirt nap. And then the the Infoblox appliance can basically continue responding to all of the offered legitimate queries because it's the network processor that's determining what's good and bad, throwing away the bad before it ever reaches the name server on the backside. So that's really the end, right? We face, unfortunately, a more varied and more hostile environment to DNS out on the internet, but the good news is that we have a lot of tools at our disposal. We have Anycast for dealing with DDoS. We have response rate limiting, which helps ensure that our name servers aren't used in DDoS attacks against other people. We have DNSSEC to combat cache poisoning attacks, response policy zones to help against the threat of malware, and advanced DNS protection, which is, of course, one of our proprietary technologies for dealing with DDoS and cache poisoning and so on. So I should explain why I have My Little Pony fan art on this slide. I originally wrote a version of this presentation for an event that we had at the New York Stock Exchange in New York. And of course, that's where the New York Stock Exchange is. But our marketing organization was making a big deal about this. You have to make sure that these presentations are as good as possible. And so I put this at the end. And they reviewed it and they sent it back to me. And they had replaced this image with a black and white photo of the US Cavalry. And I said, I like the My Little Pony fan art. And they said, not suitable for a New York Stock Exchange event. And I said, but my kids like My Little Pony. And they said, still not suitable. So I said, all right, but from now on, I'm going to use that. All right. The last thing, the very, very last thing I will say to you just briefly is that one very cool thing that we can do with response policy zones is we can actually collect query streams from people without ever having direct access to their networks. And so if you're willing to, one of the things we do as a service is if you will send us a capture from, for example, one of your name servers, a capture of the query stream, we can run that through our current RPZ data and see if there's any malicious activity on your network. We can see if any of those queries indicate that you might have infected hosts on your network. So if you're interested in that, Javier and Paco can definitely help you out. Please do take us up on that if you're interested. All right, any questions about any of this? No questions. Okay, well, I've taken up enough of your time, so I will hand the mic over, but thank you all very, very much for your attention. I really do appreciate it. Thanks.